My name's John Hocknell. Just graduated from CUNY Hunter College as a geography grad, and now I'm at the Master of Urban Planning program, also at Hunter College. I'm excited to share with you all today the work that I've been doing New York City open data and machine learning to detect cool rooftops in New York City. This is a volunteer project. It's been mentored by Madalena Romano at New York City DOC, who's here with us today. Let's get started. First, a quick primer on what cool roofs are. Roofs are rooftops that reflect a significant amount of solar radiation that they receive due to their lighter color or reflective surfaces and materials that they may have. This increased reflectivity means that less heat is absorbed by the building. On the contrary, you have roofs with low reflectivity that absorb more solar radiation. And what that does, it increases temperatures for both the building and the surrounding environment. Policies and projects in New York City, like New York City Cool Roofs, which help promote cool roof renovations and increase reflectivity in order to reduce temperatures, also reduce the urban heat island effect and reduce carbon emissions. It can also improve energy efficiency and air quality and extend the lifespan of rooftops and its equipment like HVAC. So with that in mind, first goal of this project is to use machine learning to classify the reflection of rooftops in New York City. Specifically, the idea is to use what's called image segmentation to detect cool rooftops and classify them as either cool or warm. The second goal is to quantify changes in reflection over time and use this information to find associated energy savings as a result of these new cool roofs. To pursue these goals, this project had two primary data sources. The first is the 2020 ortho imagery. This comes from the New York State Discover GIS data portal. Images are aerial or satellite imagery that have been corrected so the scale is uniform and the image's perspective appears to have been taken directly from above. This is on my machine about a little over 25 gigabytes of data for all of New York City for 2022. The second data set is the building footprints data set from New York City Open Data provided by the Office of Tech and Innovation. You can see on screen, this is the orange-ish, brownish lines of the buildings. They're represented as polygons, and there are more than 1,084,000 building footprints in this one data set. So with that, what is image segmentation itself? Data that we just talked about is used to train this image segmentation model that defines cool roofs. It's a computer vision technique that identifies and segments occurrences of objects within images. So in this case, we're looking for rooftops and then classifying them whether they're cool or warm. On the left, we have an aerial ortho image, example from that ortho image data set. And on the right is the output. So you input what's on the left and the image segmentation model outputs what's on the right. It outputs a bounding box. So as you can see, those white squares, as well as masks. So it defines the extent of the rooftops. And then it also outputs tables. So in dark blue, you can see warm roofs. And in light blue, you can see cool roofs. Models require pretty extensive annotations, and you want them to be as accurate as possible because it will result in a more accurate model that makes better predictions. This gives a decent understanding of rooftop reflection in New York City, but there are still discrepancies between the building footprints data set and the ortho imagery, which we want to rectify as much as we can in the segmentation model. So to go a little more into that, the reason why there's some discrepancies between the building footprints data set and the ortho imagery is because, as we know, New York City is constantly evolving. Building footprints are being changed because buildings themselves are being built, they're being altered, demolished. And so the data set is routinely updated to reflect these changes. On the other hand, you have ortho imagery, like what you see on view from 2022. This only represents maybe, sorry, a brief period in 2022 when these images were taken. So as you can see in light blue, this is the building footprints data set. And in the middle, we have an example of a building that was built after the ortho imagery is taken. That's why there's a discrepancy there. And then this building footprints data set was made after the buildings were demolished that are in the ortho imagery. And that is reflected in the historical building footprints data set, which is outlined in magenta. The result is through all of this and rectifying it manually, this with quite a few thousand polygons throughout the building footprints data set. And the result is the following data set that's been filtered in yellow. So for this project, I used ArcGIS Pro to filter a lot of those building footprint data sets as we spoke about, as well as for other data cleaning and visualization. For most of the rest of the project, this is all handled in Python with the following core packages: raster.io for working with rasters, shapefile for working with shapefiles, Strigly for handling the geometries, PyYAML for handling the data set file, and then GeoPandas for working with geospatial data and geodata frames. The image segmentation model itself comes from a company called Ultralytics. Their model is called YOLO, which is where you only look once, which means that you can upload a photo and the model identifies and categorizes it all at once. It's really adaptable and easy to use past pre-trained models that are ready to go. So I highly recommend it if you're new to machine learning and getting into this for the first time. Also, it's great for your own custom data sets, like in this example. So to get into the methodology, presentation and the demo mainly focus on the first goal of the project, which I spoke about earlier, is to classify reflectivity. The first step in that is to filter the building footprints data set, as we previously discussed, to fill those discrepancies. The next step is to classify every rooftop as either cool or warm. This is done using a standard remote sensing technique in which different bands of information within the ortho imagery are combined. Ortho imagery, there are 4 bands of information: red, green, blue, and near infrared. I combine these using a linear model that was developed in a paper from 2015 from Van Weiss et al. And that formula that they use is a linear model that provides a reflectivity score. The next step is to create a customized data set following the training guidelines for the YOLO model. And then finally is to train the model itself. It's done being trained. It can be used to make inferences or predictions solely on the ortho images themselves. You don't need any building footprints or annotations. The second part of the methodology, which follows the second goal, quantify changes, starts with geocoding those predictions so that they can be mapped. After that, the entire process is repeated for a previous year, such as for the 2020 ortho imagery. Doing so would then allow us to compare the changes in reflectivity over time for each building, and that can be used depending on information for each individual building to calculate associated savings in energy efficiency. All right, so in a few moments, we're going to get started on the demo portion of this presentation. So if you would like to follow along, you can this link. If you follow along at this link, it will take you to my GitHub. And if you would like to, along what's on screen, you can just to the demo folder. Everything that you need will be in the demo folder, and there is a demo.pymb file. which I will be showing you, and you can follow along with that. When we start off, like I said, we filter the building footprints data set. After we have it filtered, we want to create those annotations, make sure that everything is accurate as possible for a well-trained model. This is where we calculate the reflectivity and classify rooftops using that remote sensing technique. The visual for you to see right, you have not only the polygon outlines, but as well as the specification itself, whether it's a full roof or a warm roof. And then on the bottom is an example of what the custom training data set would look like. Is to the YOLO model and how it's trained and how it looks at these images. It basically splits it up into two different directories. So these directories correspond to each other. You have images and then labels. Image1.jpg corresponds to image1.txt in both directories. So the model will know from image1.txt what the labels are, whether it's a warm or a cool roof, and then it'll look to the JPEG image to be trained on. All right. So with that custom data set up, we're now ready to train the model itself. So the first thing we have to do is import the package from Ultralytics, import YOLO. Then we load a pre-trained model from Ultralytics, a segmentation model. There are a few of them called nano, small, medium, large, and extra large. The larger the model, the more time it takes to train and make predictions, and that requires more space and processing power. The next step is to then train the model. Pretty simple code. Doesn't require expert knowledge on machine learning or computer vision or building your own model from scratch. So if you're new, again, it's a great way to get into this. And it has a lot of really well-documented information and video tutorials online, which makes it so much more approachable. And basically, it takes that data set structure, is trained on it. All right. I will move over to VS Code to show you what that looks like in the demo file. So I will import the packages here that we spoke about earlier. If you're following along, be aware you should change your line here to follow wherever your demo folder is located on your machine. Well, just so it knows where the demo directory is. Presentation we went through in the data set. So I will skip over that for now. But to give you an example of what training the model looks like, is the code that I just showed you on the presentation. But if I run it, this is what the output looks like. The demo code, there's only a few images compared to the many thousands of images that are in the data set. So this is going to train really fast. I'm going to stop it now. So just to provide you guys an example. But as you can see here, it outputs a bunch of the parameters of the model. And down here, it'll output all of the different epochs that it goes through. An epoch is essentially one training iteration of the model in which it looks at every single image and annotation within the data set. And it continuously does this over and over again. And how many epochs you want to do. So for instance, 100 or 300. And as it goes through every epoch, the idea is that the model gets better and better over time. The next step is to make predictions using the trained model. We need to convert the pixel coordinates to geographic coordinates. The way that I did this is by using the JGW file that is associated with the JPEG. The GW file basically holds onto geographic information for the JPEG file. I read in that information and copy over. When you download these files, that geographic information comes with them. But when you're creating the data set structure for training the YOLO model, you don't need that geographic information in it because the computer vision model doesn't as a geographic data. So you don't want to be copying that and making things slower. So after we're done training the model, you move those files over just so that we can have access to them again. And the files, the JPEG, so they're easy to keep track of. Going down, run the code. As you can see, it's copying over the geographic information, and what it's doing here is converting pixel coordinates from the JPEG to geographic ones, and it's making predictions on them as well. So what I will do is I'll open up my data set, my directory for you guys, and give you a look at what that looks like. So these are the predictions in my folder for the example images that I put in this demo code. I chose a couple of ortho images just north of the Queensboro Bridge, the Queensbridge housing, NYCHA housing. I chose this area because it stood out to me on the New York City Cool Roofs map. Of the housing here participated in the program where they transformed their roofs to be cool roofs. So if I go ahead and open up these predictions, let me drag it over so you guys can see. So as you can see, there are a few examples. So as you can see here, this is NYCHA Queensbridge housing. You can see the solar panels that they installed, as well as the white rooftops. The light blue masks show what the model is predicting to be cool roofs, and then the dark blue masks show what the model is predicting to be warm roofs. As we go through these predictions, there's 9-ish images here. You can see the predictions that it's making. Okay, so back to the demo code. The next step is to combine and map all the predictions. So we have the predictions themselves, the geographic information. We want to combine that all. What this does essentially is it goes through every image, and then it goes through every single polygon within every single image, and it adds that all to one geodata frame, and then it saves that to a shapefile. So if I go ahead and run this code, this is just a quick map to show you what all of basically the predictions images that I just showed you look like when you map them. Yeah, that's the output of the model, converted back to geographic coordinates and map it. All right. So some more about the model itself and its results. These YOLO models are measured, the performance is measured through what's called mean average precision. It's a widely used metric that evaluates the performance averaging across all classes. So I mentioned earlier, this model, it predicts not only the mask or what it thinks is like the polygon extent of the rooftop, but also its type, whether it's cool or warm, bounding box. So for this model, the bounding box that it outputs, you can see example on the right here. It'll give you bounding box label as well as its confidence level. For this model, its score is 70.7% for the bounding box. And then on the bottom right, you can see score for the masks, those types of masks that it produces is 66.5%. This model itself represents about 33 continuous hours of training. With this amount of data, like I mentioned earlier, 5 gigabytes of imagery, as well as over 1 million building footprints, I think it's a pretty decent performance for such a model. And that's important too, because the processing power of your own machine so plays a big role in how well these models perform. The longer you train it for, better GPU or CPU you have, more data you're able to feed into it. It helps make it more accurate. So some more results. This is a normalized confusion matrix. It visualizes the performance of the model across classes and compares what the model predicts to what's truly there. So as you can see on the diagonal from the top left to the bottom right, pretty well with correctly predicting and cool roofs, 82% and 82% accuracy. However, it does struggle where it will predict cool roofs or warm roofs as being there when there's nothing there at all, or what is called just background. Can be improved by training the model on more images that have no roofs at all in them, or as few roofs as possible. That way the model can get a better idea of differentiating between roofs and backgrounds and images that contain those types of examples. So more generally, the model performs really well on small to medium-sized rooftops, as you can see in these examples of townhomes and family detached homes. It does well at masking entry of the roof and then determining whether it's cool or warm. It also performs well on irregularly shaped buildings, curved buildings, buildings that don't have 90-degree angles. It does surprisingly well, I think. It does struggle to accurately mask the extent of a roof is for large buildings, warehouses, airports, and similar types of large structures. Because these types of buildings are underrepresented in New York City. If you think about it, the amount of airports compared to the amounts of row homes, there are much fewer airports. So likewise to the other example, the model just has less information to train on for these represented types of examples, which therefore reduces the accuracy for those cases. So some uses for this model, discussed detecting cool and warm rooftops. It's helpful in analyzing cool roof projects and policies in the city. Like I mentioned, there's the New York City Cool Roofs program, identifying participants to transform their rooftops and renovate them. Also identify buildings not mapped or mismatches with existing ortho imagery, which is necessary for improving the accuracy of these types of analyses. And it can also be applied to any ortho image with the same specifications as what it was trained on. So that means we can go back to ortho imagery from 2020, 2018, usually done every 2 years here in New York City. Also means that when the 2024 ortho imagery becomes available, we can also to predict on those images as well. So next steps, improving the model, like we discussed, there's a few areas where it's good at, and then there's a few areas where it struggles. More processing power, the ability to feed it more data can definitely be improved and produce much more accurate results. The next 2 steps are kind of the second goal for the project, which is to quantify changes in reflectivity. This is done, like I said, by analyzing previous years and then making comparisons. And then finally, translating this into energy savings. And I think this could be done, another New York City open data set, data information where you would identify the polygons with building IDs, and that would allow you to pull in building information, which would allow you to see the building, like what its energy efficiency is and how the reflectivity would relate to that. I'd also like to point out some really helpful references for this project, and I definitely recommend checking them out if you are interested in this stuff. Of course, the building footprints, ortho imagery sets that we discussed, the New York City Cool Roofs program participants map, Analytics YOLO segmentation model. For literature that I used, Roofs in a Warm City was a huge help as a project in collaboration with Hunter College and the Mayor's Office of Climate and Environmental Justice. My professors, Mehdi Harris, worked on this, and it was really helpful in getting this project started. So the Cool Roofs dashboard, which is a part of that project, roofs from New York City Business, as well as the Van Weiss article that I recommended if you're interested in the your model used to define the reflectivity score. And that's it. Thank you all for listening and joining. Thank you so much to Madalena for mentoring this. With that, I guess we could get into the Q&A session if there's any questions.
I saw a couple of questions. Usually I give seed questions. I didn't do that this time, so sorry, John. But someone asked, Henry asked, during the training data building phase, like labeling, how do you decide which roof is warm or cool, or is it based on LST data?
The reflectivity score comes from combining the bands using the formula. The formula is from the MICE article that I mentioned. It's a linear model that combines all four bands, the blue, red, green, and near infrared. That outputs a score. And essentially, I did was similar to the Cool Roofs in a Warm City literature. They did a threshold of 60%. So any score above 60% is labeled as a cool roof. Anything below is labeled as a warm roof. I hope that answers the question.
BNAF asks, what percentage of the data is labeled for training, testing, and validation?
Demo is a little bit different for the sake of the demonstration. Everything was put into the training, but for the actual model that I trained, 70% was put into the training, it was put into validation, and then 10% was put into the thing.
Frank P asked, did you do any model optimization or tuning?
Yeah, there are a lot of options with YOLO Ultralytics package that you can play with. Experimented with a lot of them. As you can take an image and rotate it, you can take an image and flip it. You can also, there are so many different options. I did experiment with the flipping and the rotating. It's helped improve the model. Again, so many options. I would have to do a lot more experimenting with it.
Is the code publicly accessible? Godfried, John did put the link to his GitHub in there. I'm just going to put it in again. So yes, it's all accessible, and as well as all the images he used if you wanted to try this project out yourself. And bear in mind, we also put a quick list of every single environmental variable that he had on his computer. So that's what he was working with. And if yours is a little different, things may go differently. We don't know. All right. So what's next? Next question. What led you to Ultralytics? I'm curious about the cost for this option and if you considered or tested any other options or open source options. Calvin, why do you have to be a problem? I'm kidding. I'm totally kidding. I love you, Calvin.
That's a good question.
Let's skip the whole bunch. I'm sorry. I'm going to go back up, but let's answer that one first.
Okay. Yeah, no, that's a great question. I think like I mentioned, I am new to machine learning, at least for this project. Ultralytics was a very approachable package and method for doing all of this. Also, you asked about cost. It's free, so it's free to use. I'm pretty sure it's free. Well, it's free for research like this, in terms of an application gets into licensing. But for research, there's no cost. I did test other options since you can find models out there through ArcGIS Online and Esri that they have models for detecting just the building rooftops, not if they're reflective or they're cool or warm. They have models that detect buildings. What I found is that they're more generalized. So for example, they'll be for the entire USA or trained on the entire USA. I think for New York City specifically, we have some interesting and unique structure that is different. We have a lot of we have a lot of homes and roofs and buildings that are different types than what you find in other parts of the country. So the ability to train the data set on just New York City for New York City application, I think really helps improve the accuracy and the end result for what you want to apply it for.
Okay, so let me just jump on back. I think Calvin might have answered this question for us. Where did the building outline data set come from? It came from Open Data, and there is a link to it in John's presentation. I believe Calvin said the same. So I don't know if Baltimore has the same, but if not, OpenStreetMap has something. I would also advise that if you go to OpenStreetMap, OpenStreetMap is fantastic anywhere where there's a large city. But the minute you go out to more rural areas, it becomes a lot more sketchy. So if Baltimore has parcel data of any kind, because the building footprints and part and parcel, that's not what I say it, part of tax lots. So if you have tax lots and they have tax blocks, it's likely they'll have building footprints. I don't know if they will, but if they do have it on OpenStreetMap, then the chances are it does exist somewhere. But I would definitely say look into it for Baltimore. All right. And thank you, Calvin, for the kudos and all the help. What else? Okay. Adrian Nesta says, this was awesome, John. Thank you for sharing. I know you mentioned this at the end, but this would be super interesting to somehow geo-join the polygons onto New York City building data as energy efficiency benchmarking. That's also on New York City Open Data Portal, if I'm not mistaken. I think, and Adrian, I could be wrong, but I remember John and I looking at that building and energy water data, and it's only for a specific year, unless that's changed. Oh, where did this come from? 2022 is the present. The ones I was looking at said 2013. Okay. So, John, take heed of that link.
Definitely. Yeah. Thank you.
Because when we were looking at it, it had the wrong link on it. Okay. You're good. All right. Let's see. Someone added the building data footprints. Thank you so much for doing that for me, for John. Sean, I remember what's very interesting. Please share the link to the paper. Did you? And you shared the link to the paper already. Thank you, Nasuka. Okay. Doesn't have her. Calvin. Oh, Calvin found it. Thank you. Calvin, you're awesome. Calvin Brown works for DOT, and he is great when it comes to data. Yeah, I did see previous years, but that's all I saw. I did not see the 2022 to the present data. All right. Oh my God, everyone's like, all right, let's make it about Calvin. It's supposed to be about John. But we are at 15 minutes too, and I did not put in any seed questions. But for those that might be interested in following along that didn't, John, what did you use as your platform for developing this? Ultralytics, I'm assuming, rather than TensorFlow or anything else? So if someone wanted to do exactly what you did, what did you do it in?
Yeah, so everything was coded in a Python 3 environment, it's code and Jupyter Notebooks package. Yes, I used Ultralytics YOLO for the image segmentation model and training, and creating the custom data set that I created is according to what their model, how it's trained.
No, thank you for that. But I was wondering, what did you do to visualize the output of those packages? Because obviously, if you're testing something and training something, you want to see where it's going wrong. So did you just visualize it within Jupyter Notebook?
Yeah. So for example, the images that I pulled up, that's the direct output of the YOLO model. Those are the images that it outputs for you when you make a prediction. That has the dark blue and the light blue masks that I showed.
And that's directly from Notebook.
Yeah, or it outputs to your folder, and then you could bring that into the notebook if you want. And then when I converted that to geographic coordinates, you can, of course, display that however you like using geodata frames and plotting in your notebook. You might also use it in ArcGIS Pro just to view around in there as well and make sure things look good.
Okay. So I wanted to see if anybody else had any questions. Dimitri said, be free to unmute you unless you want to just drop it into the chat. If not, that is also cool because this data is up on his GitHub, and you can feel free to reach out and contact John with any questions. And any questions that you may have here are also cool, because that just means we will need to, I'm sorry. We will try to update these frequently asked questions on the GitHub as well. John, I think if you want to wrap up, you can wrap up.
Yeah, I just put in the chat my email and the link to the GitHub again if you would like to contact me or take another look at the demo code and the code that I have in the repository. But yeah, thank you all so much for joining today and learning about cool rooftops and machine learning. It's been a pleasure. Thanks, everyone.
Bye, everyone. Stay